Hey, Professor, I don't think people can hear you. I know I can't.
Hello, can you hear me now?
Yeah,
Yep.
yeah, I can.
Can you hear me? Okay, good. Okay, thank you. In the previous lecture, I mentioned the definition of integer program. Let me see here. I mentioned the definition of integer program, and also we mentioned the importance, right? Because using this logic, using this extra binary or integer variables, I can what? I can actually express the logic. Once I can express the logic, then it becomes very, very practical because I can use this technique to model many, many real life problems. Although a commercial solver, even let's say Excel, can help you solve the problems, but nobody can model it for you. So this may be one of the most important lecture in the whole semester. And then I introduced the two illustrative examples. The first one is a set covering problem, and the second one is where the second one is an assignment problem. Okay, both of them. In both of them, we use binary decision variables to denote the logic here. And we also mentioned an either/or condition. So either/or is equivalent to something that I'm gonna mention in the beginning of this lecture, which is choosing k out of n. Either/or means I'm gonna choose exactly one out of two. So if you have an either/or in general, for example, f1x less than or equal to 0 or f2x less than or equal to 0, you can formulate it in this way. And be careful that when delta equals to 0, that means you choose the corresponding one. For example, suppose delta 1 equals to 0, that means you choose to satisfy, excuse me, you choose to satisfy f1x less than or equal to 0, okay? So here we showed an example. Here we showed another example about auto company, manufacturing the decision. And here I have, oops, here I have applied the logic here because we know that x1 means the number of cars to be produced. So x equals to 0 is equivalent to x equals less than or equal to 0. And hence, this immediately becomes an either/or type constraint. Why? Because here I mentioned if a size is to be produced, then at least 1,000 cars of that size must be produced. That means either, where's my mouse? Okay, that means either xi is less than or equal to 0 or greater than or equal to 10,000. Sorry, 1,000. So you can immediately follow in this way, okay? And in this problem, we can simply take m equals to 4,000. Why? Because m is the upper bound of these two functions. Function 1 is xi. Function 2 is 1,000 minus xi. So 1,000 minus xi is clearly smaller than 4,000. But how about xi? Because I have the total steel supply limit is 6,000, while per car of compact size costs you 1.5 ton of the steel, so that at most I can build 4,000 vehicles in terms of compact. And not to mention mid-size or large, it's even less. So that 4,000, it is safe to take 4,000 as your upper bound. Okay, uh, and then we're going to introduce k out of n today. I know I already mentioned a little in the end of last lecture. So for the k out of n, we use exactly the same logic as the either/or conditions. Here I have delta 1 to delta n because I have totally n such constraints, such requirements. And I'm gonna write a condition such that k of them must be held. So the same thing that I'm going to use delta I equal to 0 to indicate that the ith constraint is satisfied. For example, suppose delta 1 equal to 0, then you have f1 as less than or equals to 0, right? That means this constraint is satisfied. Okay, one very important thing is that the summation of delta must be equal to n minus k rather than k. Why? Because again, delta I equal to 0 means it is satisfied. So how many constraints must be satisfied? K of them. So that you should have k zeros. In other words, you should have what? N minus k ones. So that delta 1 plus blah, 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 plus delta n equals to n minus k. Okay? So here, as an easy exercise, what if I want to say at most or at least k of them must be held? So let's see the at most one first. I think I introduced this in the last lecture. At most, let's say, what is this? Let me make it bigger. 13. Oops. What's up? Did I put 13 here? Oh. Here, piece 13. So if it is at the most k, then I'm gonna have what? First of all, I still have all these constraints the same, okay? Let me build an equation and the bracket so that I have. Still, you have, let's say, f1 x less than or equal to m delta 1. Let's make this. And then I'm going to copy and paste. Until fn delta x less than or equal to delta n. Then the problem is here. Delta 1 plus delta 2 plus blah, 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 plus delta n should be what? Because we say at most k of them must be held. In other words, what? In other words, I must have at most k zeros, right? That means the summation of deltas should be what? Should be at least n minus k, right? Okay, and finally the same. I have delta I. Okay, let me be consistent to the lecture notes. Delta n is in 0, 1. Okay, so the important part is here is less than or equal to n minus k. And very similar, if I wanna say at least, I should have what? I should have greater than or equal to n minus k. Why? Because the similar logic that at least k, that means I should have at least k zeros. That means n minus, give me 1 second, at most, sorry, my fault. This should be greater than equal to. If it is at most k, that means I should have at most k zeros. That means the summation of deltas should be at least n minus k. That means that's greater than or equal to n minus k. Yes. If it is the case, at least k of them must be held. That means at least I should have n. At least I should have k zeros. That means the summation of deltas should be at most n minus k. Okay. In other words, there are at most n minus k ones. Then yes, that's correct. Any questions here? All this about the logic. The important thing is that you need to know that here delta I equal to 0 means that constraint I is selected, not equal to 1, as you know we usually use. Any questions? No? Okay, let me make it bigger. The next one, the formulation that we're going to introduce is a function with n possible values. That means suppose I have a function fx and I have n values to choose for the fx. My fx could be b1 or b2 or bn, blah blah blah. So in this case, I can formulate it in this way: fx equals to b1 delta 1 plus blah 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 plus bn delta n, where the summation of deltas should be equal to 1, and the deltas are again extra binary decision variables. So in this case, what does it mean? First of all, the summation of deltas equal to 1. That means what? That means I can choose exactly one delta I to be 1, right? Because delta i's are all binary. And then I set fx equals to b1 delta 1 plus blah 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 plus bn delta n. That means what? That means fx has exactly one choice of the values, which is one of the bi's here. So this guarantees that the value of your xi must be exactly one of them. As an example, let's have a look at the set covering problem. So here, for example, I think it is about fire station building, right? Let me see. Right, building fire stations, okay, to determine where I should build a fire station. Okay, but here, suppose the government decided to build totally, let's say we have 10 towns, and suppose the government decided to build totally 2 or 3 or 5 or 8 fire stations. In other words, you cannot have any other values to determine how many, stations. For example, you want to say, I want to build 4, I want to build 1. No way. You must build either, no, not either. You must build 2 or 3 or 5 or 8. So we use the same notation to in this model. So I use xi to indicate whether there exists a fire station to be built in town I. And here I suppose that I have 10 towns, so that the summation of xi's from I equal to 1 to n means what? Means the total number of fire stations built, right? And this equals to 2 delta 2 plus 3 delta 3 plus 5 delta 5 plus 8 delta 8. That means the total number of fire stations must be exactly one number among them, 2 or 3 or 5 or 8. And then I use the same way here: delta 2 plus delta 3 plus delta 5 plus delta 8 equal to 1, and all deltas are 0, 1. So in this way, I can easily formulate this logic. Be careful here. I didn't use, for example, delta 1, 2, 3, 4. Instead, I use delta 2, 3, 5, 8. It's just a notation. I use this way because it's easy to find the meaning, the corresponding meaning. For example, delta 2 means the value equal to 2. Delta 8 means the value equals to 8. If you like, you can of course use delta 1, 2, 3, 4. There's no problem. Again, this delta I is just a notation. You can also use, for example, A, B, C, D. It doesn't matter. It's just a notation. Okay. Any questions? No. By the way, in some practical problems, this can be applied. For example, you have several choices of one schedule. For example, you can choose, let's say, the number of people to be hired to be, let's say, an even number or an odd number due to some budget limits or due to some requirements. And also you can choose, for example, suppose I want to hire, let's say, people to do one work, and I want to keep, let's say, the balance of the genders, so that you can choose, for example, the female workers, the number of female workers must be equal to the number of male workers. And then, for example, suppose you have a budget, let's say, to control the number of, let's say, a male or female workers, then you can use this way to correspondingly write the conditions. Okay. Any questions? No. Okay. Let's have a look at the next one: dependent variables. So dependent variables means one of the most common cases is if yi equal to 0, given that yi is a binary variable, then x is less than or equal to 0. In other words, the value of x depends on y. This x could be a continuous variable or an integer variable. It doesn't matter. But this y is a binary variable. In this case, we can formulate it as x is less than or equal to my. and this m is a big M, is a big number. Still remember we used the big M notations here in, let me see, which lecture? I remember lecture 5, I think. Simplex method 3. Still remember here, we used the big M method to find what? To find an initial initial basic feasible solution to start your big M, to start your simplex method. Remember this one, the big M method. Okay, so here the big M uses the same concept here, but not the same thing. It's different things. Here is for modeling. The one used in the big M method of the simplex method is to find an initial basic feasible solution. Okay, but here M is also a very, very big number. M can be defined as the upper bound of X, so that if y equal to 0, then your X must be equal to 0. Why? Because, no, I should say X must be less than or equal to 0. Although in most cases, X less than or equal to 0 means X equal to 0. If my y equals to 1, then you have X as less than or equal to M, because M is the upper bound of X. So this constraint, is always satisfied. Okay. In general, we can say that y is in z plus. Z plus means positive integers or 0. But in real practices, most problems, you have y equal to, y is in binary variables, the set of binary variables, and X is greater than or equal to 0. As an exercise, what if I want to formulate fy equal to 0, then X equal to 0, given that X is greater than or equal to 0? This is really simple, right? Because X greater than or equal to 0 is equivalent to what? Is equivalent to, X equal to 0 is equivalent to X less than or equal to 0. Why? Because it's given that X must be greater than or equal to 0. So in this case, the same. You can still use this formula to write it. You know what I mean? So for example, suppose y is whatever number, let's say 1, 2, 3, 4, 5, because here I limit y to be any positive integers. It doesn't have to be 0, 1. But the same. Why? Because if X is less than or equal to 1m, then of course X must be less than or equal to any, let's say km, where y equal to k, any integer number. So no matter which case, no matter what value y is, any non-negative integers, this one is always correct. Okay, so this case, this case is equivalent to be formulated in this way, exactly the same formulation. Let's have a look at an example. So suppose in the auto manufacturing example, I add one more condition, that to start producing size I auto, there is a fixed one-time fee. That is F1 equal to 20,000, F2 equal to 40,000, and F3 equal to 70,000. Let's go back to the problem here. It's going to be more clear. So again, this problem, but I have a constraint that if I plan to build one size of the vehicle, I will have a one-time fee. It's easy to understand. For example, I want to buy some, equipment, machines, and also hire some workers, to start to initialize my production line of, let's say, compact or middle size or large size, vehicles. And the initial fee, one-time fee, initialization one-time fee for the compact vehicle is $200,000. For the middle size is $400,000, and for the large size is, how much I forgot, as F3, as $700,000. Okay, and then I ask to formulate the problem. So here we can denote yi, a binary variable, to be if size I car is to be produced. If it's 1, then it's going to be produced. 0, then otherwise. And then if size I is not to be produced, then I must have xi equal to 0. Here, xi must be greater than or equal to 0. Why? Because it denotes the number of vehicles. You cannot build, for example, -1 vehicle. It's meaningless, So we can add the new constraint like this way. Xi is less than or equal to yi, and y is in 0, 1. This means what? This means, again, the dependent variables, exactly the same here. See it? If my y equal to 1, that means size I car is to be produced. Then I have xi is less than or equal to m. Again, m is the common upper bound of the manufacturing car. That means for any x1 I equal to 1, 2, 3, all of them must be less than or equal to m. It's the upper bound. And my yi is a binary decision variable. And we also need to change the objective function. Why? Because it is not simply in this way, which is, it's not simply here. This is what? This is our profit function, remember? Which is here. Let me see that. So in this example, this is our profit function because I want to maximize my profit, right? And the profit function is here. Now we have one-time fee, initialization fee. And if I'm gonna start to produce compact vehicle, I need to cost 200,000 in the beginning. So that you need to subtract 200,000 of Y1 and do the same for Y2 and Y3. And this new function indicates the new profit function, okay? And we're gonna use this one to be the objective function. Now, the complete model of this problem can be formulated in this way. First, the new profit function. And here, let me draw boxes here. All these constraints are still the same as we used, indicating the steel limit, labor limit. And this one indicates what? Either 1,000 cars or 0 car, you know. And then here, this is the constraint plus this. These are the constraints to denote whether car size I will be produced or not. If it's going to be produced, then I need to pay for the initialization fee. If it's not, I don't need to pay. And correspondingly, x is going to be 0. Then let me ask you a question. Here I have delta. Here I have y. Is there a way I can actually merge delta and y? Any ideas here? Again, what does this delta I1, delta I2 mean? This means, well, you are going to make a choice whether xi is going to be 0 or not, right? If xi is 0, then you have delta I1 equal to 0 and the delta I2 equal to 1, right? If xi is greater than or equal to 1,000, why? Because as we mentioned here, in the original problem, if a size is to be produced, then at least 1,000 cars. You cannot produce, let's say, 100 cars. No way. Again, for economic reasons. In other words, if a size is to be produced, then first I need to produce at least 1,000 cars of that size, and second, I need to pay for the corresponding initialization fee, right? So actually, you know what? These two are the same. Delta I and I1, I should have said delta I1 actually. Yes, I2 is different. And yi are exactly the same. They equal to 1 means what? Means size I, give me 1 second. Delta I, yi equal to 1 if size I car is to be produced. And delta I2 equal to, delta I1 equal to 1. That means size I is to be produced. Yes. So in other words, let me make it smaller. In other words, P17, you have what? You actually have yi equal to delta I1. Why? Because yi equal to 1 means size I is to be produced, right? And for the same, for if I have delta I1, if my delta I1 equal to 1, that means what? That means this one is 1 and this is m, right? That means, give me 1 second. Delta I1 equal to 0, that means it's not, I should say, It's not going to be produced. Yes, if delta I1 equal to 1, that means delta I2 equal to 0, right? And it means that your xi must be greater than or equal to 1000. That means size I is to be produced. Okay, so they're the same. In other words, you don't have to define a new decision variable yi here. You can simply make this one I, replace this one by the delta I1. So in this case, you can save actually n integer variables, 3 integer variables, I equal to 1 to 3. You don't have to use this yi. Instead, you can just put the delta I1 here. Any questions here about the dependent variables? And you're going to see a lot of cases in practice. For example, suppose you are a manager. Let's say you're a CEO of the company. You want to determine whether you want to, let's say, create a new department. Then simple. If you want to create a new department, first you need to pay for the initialization fee. And the second thing is that if you want to create a department, you need to what? You definitely need the department to be operating, right? Meaning that it will, take at least, let's say some levels of the work. You are not gonna, let's say, create an empty department, without doing anything. So what's the point, right? So in this case, it's also a dependent variable. In other words, you're gonna ask whether the department is gonna be created or not. And then if it is created, then the workload should be at least something, and you should pay some initial fee. Or let's say pay some additional salary to each person. So this is dependent. And also when you are making some decisions, especially this kind of time-related, time-variant stage decision, it's also going to be dependent. That the stage of t depends on the stage of t minus 1. And in practical cases, you're going to see a lot of such dependent variables. And in the homework, I'm going to also give you some examples about dependent variables. This one is one of the most widely applied in real life. Okay, and after it, I'm going to introduce some simple modeling tricks. So one of them, oh, by the way, any questions about the dependent variables, including the practical problems, not only the modeling itself? No? Okay. In the next thing, we're going to introduce some simple modeling tricks. The first one is a linearization of absolute functions. Absolute functions means, suppose I have for example, fx is less than or greater than or equal to something. And how to formulate this? How to linearize this, actually. So for the case that absolute value of x is less than or equal to y, of course your y is greater than or equal to 0. This is relatively easy to be formulated. Why? Because absolute value of fx, that means the maximum of fx and the negative fx, right? If fx is greater than or equal to 0, then absolute value equals to itself. Otherwise, it equals to negative fx. So that means the maximum of fx and the negative fx is less than or equal to y. That means what? That means simple. Both of them are less than or equals to y. So that you just simply list them together, that fx is less than or equals to y, and negative fx is less than or equals to y, and you are done. This is very simple. The second case is a bit more difficult, that I want to formulate absolute value of fx is greater than or equal to y. Then here's the problem. Because I cannot use this logic or directly use this logic to formulate the maximum of them is greater than or equal to y. How can you formulate? You cannot say that both of them are greater than or equal to y. For example, suppose fx equals to, let's say, 5, and y equals to 3. So very clear, I should have phi is greater than or equals to 3. You cannot say negative phi is greater than or equals to 3. It's wrong, right? So in this case, we have to create some binary variables. The problem can be directly modeled here in this way, by these 4 extra constraints, where delta is an extra binary decision variable. So the logic is in this way. Suppose your delta equal to 0. you substitute into 1, 2, 3. What you're gonna have? Equation 1, constraint 1 is gonna tell you negative fx equals plus 0 greater than or equals to y. That means negative fx is greater than or equals to y. Constraint 2 becomes fx plus m greater than or equal to y, because delta equal to 0, right? And m is the upper bound of absolute value of fx. It's a very, very, very big number again. So if I have fx plus m is greater than or equal to y, that means what? That means it's always satisfied, because again, m is a big, big, big number. We know that fx is less than, okay, let me write it down here. Page 18. M is an upper bound of fx. So this gives you that your fx, this gives you that your fx is always less than or equal to m for any x, right? And you also have fx as what? Greater than or equal to y. So that, of course, I have m is greater than or equal to y. So this one is always correct. The second constraint, fx plus m is greater than or equal to y. It's always correct. And then the third constraint is going to give you what? It's going to give you fx is greater than or equal to negative m and less than or equal to 0. That tells you what? That tells you that if delta equal to 0, it is corresponding to the case that your absolute value of fx equals to negative fx. In other words, your fx is negative. Okay, so I summarized here the meaning of constraint 3, 2, and 1. And if delta equals to 1, let's see what do we have. We're gonna have constraint 3 becomes what? Becomes fx is less than or equal to m. Of course, it's always satisfied, and greater than or equal to 0. And constraint 2 becomes fx is greater than or equal to y. And f1 constraint 1 is negative fx plus m is greater than or equal to y. This is nothing. Why? Again, because m is a huge number. So fx m minus fx is greater than or equal to y. There's no problem. So in this case, it tells you what? It tells you that fx is greater than or equal to y. That means what? That means when delta equals to 1, then my absolute value of fx equals to fx. That means your fx is positive. So it's non-negative. So in this case, I use an extra binary decision variable delta to indicate the two cases. Fx is positive, as let's say negative, or fx is non-negative. In no matter which case, it's included here, so that I can claim that these 4 constraints is equivalent to claim that absolute value of fx is greater than or equal to y. Okay, this is, I know it's not that easy. You need to carefully think about it after the class. And then you're going to understand it, especially constraint 3. The constraint 3 is a kind of like a common constraint in many, many problems to control a choice, something similar like this way, as whether case 1 or case 2. And the difficulty of formulating these 3 constraints is when one case is satisfied, you need to guarantee that the other case will not be violated. In other words, for example, suppose delta equal to 0, you're going to have fx is less than or equal to 0. No problem. That tells you that fx is not positive, right? In other words, you must have you must have absolute value of fx equal to negative fx. However, you need to guarantee that the other side is also correct, which means here you should not have a contradiction. Here, if delta equal to 0, I have what? I have fx is greater than or equal to negative m. It's correct. However, if you're careless, for example, you write this part as fx is greater than or equal to negative m delta, then it's going to be wrong. Why? Because you're going to have fx is greater than or equal to 0 and less than or equal to 0. That means your fx is forever equal to 0. This is clearly wrong. In many practical problems, it's not very easy to find, something like constraint 3 that you guarantee both sides are correct. It's not that easy in many, many cases. Any questions here? I know this one will take you some time because in my previous teaching, many students have a lot of questions here. I know here because we're having the online study. Maybe it's not that easy for you to immediately digest this part of the knowledge. Please do have a look at this part after the class. And if you have any questions, please feel free to contact me, okay? I do have office hours, the same office hours actually, or you can simply shoot me an email. Now it's, it's a special time. I think I have plenty of time to answer your questions. That's something good. Okay, let's have a look at the last case that I'm going to introduce in this lecture. The last two cases actually, which is to linearize nonlinear functions with finite-valued integer variables. Here, what I mean is that some integer variables with very limited finite values. For example, you have in this case x is in 0 or 1 or 2, y is in 2 or 3. You cannot have a very, very large size. For example, x is in 1 to 1 million. Then this method does not work. Okay, let's have a look at one by one. First of all is a linearization of expression of x, y, where both x and y are binary decision variables. So first of all, this is nonlinear, right? But since they are binary, I can easily linearize it. Why? Because because x, y equals to 1 if and only if both of them are 1. As long as one of them are 0, x, y must be 0, right? So the constraint, the constraint that xy and xy is in 0, 1 is equivalent to this. Z is less than or equal to x, and z is less than or equal to y, and z is greater than or equal to x plus y minus 1, where xyz is in 0, 1, which means all of them are binary. So here z indicates the product of x and y. Why this one is correct? First of all, have a look at here. The first two constraints, z less than or equal to x, z is less than or equal to y. That means what? That means as long as one of them, x and y, is 0, then z must be 0, right? But if both of them are 1, here z from only constraints 1 and 2, you cannot determine z is 0 or 1 because both are satisfied. Then constraint 3 tells you that in this case, z must be 1 because z will be greater than or equal to 1 plus 1 minus 1 is equal to 1. So that z must be equal to 1 because z is binary. And then let's have a look. What if x and y, one of them is 0, the other is 1? Then from here, the third constraint tells you z is greater than or equal to 0. And from constraints 1 and 2, you have z is less than or equal to 0, so that z equals to 0, right? And what if both x and y are 0? You're going to have from constraints 1 and 2, z less than or equal to 0. And from constraint 3, you're going to have z is greater than or equal to -1. Still no contradiction. So you still have z is equal to 0. This constraint 3 is something similar to the constraint 3 here. You see the point? Again, the key is that you're going to build a constraint such that first for the case you are discussing, for example, x, y, both of them are 0. This one is satisfied. These are satisfied. And the second thing is that in any cases, none of them will be violated. In other words, you're going to discuss 4 cases, x equal to 0, y equal to 0, and x equal to 1, y equal to 1, y equal to 0, and x equal to 0, y equal to 1, and both of them equal to 0. No matter which case, none of them will be violated. That's the trick and also the difficulty to define such variables. And the second example is the case for x times 3 to the power of y, where x is in 1, 2, and y is in 2, 3. So here, because the size of x, the solution size, let's say the feasible size of feasible region of x and y are very small. Totally, they're only the combination only 2 by 2 equal to 4 cases. So I can simply list all combinations and define a new binary decision variable corresponding to each combination. So for example, I can define a delta 1, 2, 3, 4, where delta 1 equal to 1 for x equal to, for the case x equals to 1 and y equals to 2, so that I have x times 3 to the power of y equal to what? Equal to 1 times 3 to the power of 2 equal to 9. And the delta 2 equals to 1 is corresponding to the choice of, or the combination of x equals to 1 and the y equals to 3, so that this value equals to 27. Delta equals to 3 for the case of x equals to 2 and the y equals to 2, and the value equals to 18, and the delta equals to 4 to indicate x equals to 2 and y equals to 3, so that the value equals to 54. And then I can use what? I can use this case function with n possible values. In other words, here, this function has what? Has totally only 4 values to be selected, right? They are going to be 9 or 27 or 18 or 54. So this is equivalent to this group of constraints: 9 delta 1 plus 27 delta 2 plus 18 delta 3 plus 54 delta 4. And the delta 1, 2, 3, 4, the summation of them equals to 1. And all of them are binary decision variables. So that here, it forces you to make a decision which delta equals to 1. And that there must be exactly one delta I equals to 1. And the corresponding meaning we can find here. For example, suppose I have delta 3 equals to 1. So delta 3 is here. It's corresponding to the choice that x equals to 2 and y equals to 2. And the same for other cases, okay? And again, this method works only for the cases that the solution space or the feasible region of all these variables are small. If suppose, for example, your x equal to 100 and have 100 choices, and your y also has, let's say, 100 choices, then the combination will give you how many choices? Will give you 10,000 choices. Nobody's going to use this method, okay? Any questions about the tricks here? No? Okay. After this class, before we start class 3, before we start class, not class 3, I want to say the class on Wednesday, actually. Before we start lecture 9, please do have a review of this part, this lecture 9. It is very, very important, and it's super, super practical. Later, you may forget what simplex method is, but please remember these modeling tricks, because really no computers, no software can help you do this. If you want to, let's say, hire someone to do the work, it's pretty expensive. It's really, really expensive. I can guarantee you. For example, if you want to hire a modeling group and then also do some numerical analysis, some professional team from Google, even a smallest project is going to cost you almost $100,000. Not kidding, $100,000. And for some simple works, you can do it by yourself, just by the tricks that introduced here. Okay. In other words, if you can really understand the part very well and add some practice later, you already earn $100,000. Anyway, just a joke. But indeed, this is very, very important. Okay. Let me go back. Okay, now you can see me. Thank you very much for today's lecture, and I have office hours today from 4:30 to 5:30, I believe. If you have any questions, please feel free to contact me. Thank you very much, and see you on Wednesday. Bye-bye.